Welcome to the Duke Data Science entry into the 2018 FICO Data Challenge. We wanted to create a global model for this challenge that had pure modern machine learning under the hood, but that looked on the surface like it was really traditional, similar to the kinds of models that people designed before machine learning was invented. So we ended up calling it a two-layer additive risk model. And then we created two kinds of local models, even though the global model is completely interpretable. We have rule-based and case-based explanations. So let's go. So let me tell you about our global model. The global model is as accurate as any neural network we found, but it's meant to look and act like a traditional scoring system with subscales, similar to models used as far back as the Burgess model of 1928 from criminology. And these kinds of models are also used pervasively throughout healthcare. So the model is very interpretable, but also highly nonlinear under the hood, as you'll see. Now the interface allows the user to input their own values for the features, but there are 23 original features. So if you don't feel like entering all of the feature values, you can just use one of the three people that we have just as a demo programmed into the interface here. Now, when you click Run Model, it converts the 23 features into 180 binary features and calculates all the subscales and all the risk estimates. And it does take a few seconds sometimes because it has to run some mathematical programming. Now, the final estimate is over here. And you can see that this guy has a 95.2% risk of default, so he's very risky. Now there are 10 subscales, and they're listed over here. And each subscale comes from just a few of the original features. So for instance, this subscale comes from just one feature, whereas this subscale comes from these three features. Now, each subscale is designed to be its own miniature model. And what I mean is that there's a risk estimate from each subscale that you could use on its own as if you didn't have any other information. And the subscales get combined later to produce the overall risk score. So the pop-up window shows the full computation from the original features to the output of the subscale. There's no nonlinearities hidden in here. Here the external risk estimate feature value was, I think it was 61, so it fits in this interval, and so the person gets 1.79 points for that value, and then a bias gets added to it, and then it gets sent through a sigmoid to produce a probability, which in this case is 81.9%. And that's the output of this particular subscale. So it's its own miniature model, and it's pretty easy to explain to a client how each of their risk scores was computed. And some of those subscales, as I mentioned, involve multiple features. Like this one has 4 features. And then again, the features are converted into points through this piecewise nonlinear transformation, and then gets added with a bias term, and then gets translated into a risk probability of default. Now, by construction, the model respects monotonicity constraints. So, and these are labeled next to each of the features. So if you want to change one of the features and rerun the model, you'll see that that things change monotonically. Now, green, by the way, means less likely to default. Okay, so we'll put it back, I guess. Now, the final model that combines all the subscales is over here. So this adds up all the points from all the subscales and weights them by these weights. So it's the subscale scores multiplied by the weights, and then that's the total number of points. You add up the points, and then add it to the bias, and that translates again into an overall risk of default. Okay, so that's it for the global model. So, all the calculations are completely transparent. We didn't hide anything. It's all totally verifiable, and you can see how all the terms are contributing just by looking at all of the different colors. Now, at the bottom, we have a set of risk factors that are heavily contributing to the final prediction, and it tells you what subscale those values come from. Like this is, 48 or less. And then the rule-based explanations are created by solving an optimization problem. It's a mathematical program for a minimum set cover problem, which was just done using Gurobi on our machines at Duke when I clicked Run Model. And this provides high support rules that are completely faithful to the global model. So here it says that for all of the 594 people whose external risk estimate is 63 or less, and the average months in file is 48 or less, all of those 594 people were predicted to default by the model. Last but not least, we have case-based explanations, where the top line is the current individual, and then these are the cases closest to that individual on the features that actually matter for classification. Now here, all of them are predicted to have bad credit by the global model. One of them did repay their loan. And you can see that all the features that really matter are very similar to the current case. So the features here are listed in order of how important they are. But you can see that these other individuals have important features that are close to those of the current case. And now if the box is gray, it means that this case's feature is very similar to the current individual's feature value. In fact, it's so similar that it gives you the same number of points in the global model for the two values. Because again, the global model is piecewise constant. And then these two features highlighted here are the ones used in the rule-based explanations. Okay, so that's it. I provided a global model that's actually highly nonlinear in the original features, yet compartmentalizes, so it's still transparent. Provided two types of explanations that are completely faithful to the global model. And we hope you enjoy using it. Thank you.